So we have substituted the 16 different values, right, into the equation, right? And when we solve this, the answer that I'm getting is 3.5924. Okay, so many uh, bits per symbol. So if we get h of s as 1.79 something, into 2 will come approximately 3.59. So I can say that this, therefore, the h of s square will be equal to 2 times h of s. All right, so hence we can verify this particular uh, point. Okay, all right. So this is the one important question. They may go up to show that h of s cube equal to 3 times h of s. Okay, so that's also possible, right? We should be able to solve. Very similar fashion. I just have to extend the symbols into the groups of 3 symbols. Like, right? If you have m1, m2, m3, so I'll write m1, 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 m2, and so on. Like that, right? All the combinations, and then we need to solve. Okay, so let's move further then. Right, the next topic is Markov model of information source. Okay, so far whatever we discussed about the information source is that the symbols were assumed to be statistically independent. The present symbol has nothing to do with what was the previous symbol or the symbol before that, or right, any symbol before that. Correct? So this is what we assumed so far. But you see, in practical case, right, that's not what's going to happen, right? There is what is called as the intersymbol interference. We know that intersymbol interference in the sense, right, every symbol affects its neighboring symbols. So because of the ISI present in our communication system, right, the practical information sources are not going to emit, they will never emit the statistically independent symbols. They will emit the symbols in such a way that occurrence of any symbol depends upon whatever the symbols, right, they were emitted in the past. Okay, right, so that's the change now we are going to look at, and that kind of modeling is what we refer as the Markov, right, model, or Markov model. Fine, so this is the point. The real life sources, real life sources means no statistically independent symbol emission, right? This is because of the fact, right, due to inter-symbol interference. We know about this, right? Again, we are looking at the information theory related to the communication system. So in communication, we are well versed with the word inter-symbol interference. So this means, now since there is a inter-symbol interference for each and every symbol that has been emitted or sent by the source, now we can make a statement, right? The occurrence of, let me write a symbol that's xi in, say, in any position. I'll write 0th position, in the sense this is the first symbol, let me assume, right, at 0th position in the sense it's a current symbol. Okay, so time t equal to 0 in signals and system, we have studied that. That's a current situation, right? The present time is t equal to 0. If it is a discrete case, n equal to 0. That's why we are representing xi in the 0th position. uh, Occurrence of xi in 0th position, uh, I'll write s naught. Okay, s0 is the 0th position. S naught of the message. Basically it depends upon the previous q symbols. Okay, and okay, the source is specified by using, now you see, whenever we have a source emitting certain symbols, we try to define the probability associated with the symbol, correct? But now you see, we have to specify the source by using not just probabilities but the conditional probabilities. Okay, specified by using the conditional probabilities, right? So how do you represent a conditional probability? Probability of getting a symbol xi, provided my past symbols are, you can write s1 s2 dot 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 up to sq, all the past symbols are given. What is the chance that currently right now you are going to get the xi as your symbol? Okay, so now here we can see that xi is the symbol in 0th position, right? And there are m different possible symbols, let's assume, right? So xi is the current symbol that you are going to get, or you can say that 0th position, right? uh, the source s is the source having uh, m symbols, right? It can generate any m symbols in the list, like x1 x2 dot 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 up to x, say m. There are m different symbols, so each symbol will have a probability. You see, if at all those probabilities were those symbols were statistically independent, we used to write simply x1 has a probability p1, x2 has a probability p2, etc. But now we are not writing that, right? So you see the difference, right? I am not able to write m symbols having the probabilities directly p1, p2, p3, pm. No, we are not writing that, because exist the if you want to check that what is the probability that x1 comes, you should know what are the past symbols, because current symbol depends upon the past symbols. All right. So here, if I write p of xi, right, depends upon the past q symbols. So this is a, right, we can see that there is a memory coming into picture. The what you call, the source has to remember what were the past symbols, right? Only when you know the past values, past symbols present, you can calculate the corresponding conditional probability, so that you can represent the symbols, you can calculate the symbols probability. Okay, now, so the one important question here. Okay, let's say somehow we know the conditional probability and everything related to the probability concept. We know we have calculated. Let's assume. How do you calculate the entropy? How do you calculate the information rate? How do you calculate the average information per symbol? Right. So these things we know how to calculate whenever the source is emitting the statistically independent symbols, or whenever the source is memoryless, that has no memory, directly it keeps on emitting at random, right? We know that. Now the same parameters we should be able to calculate for the Markov source, which has the memory. Okay, so that's what we are going to look in this section. Okay, so this is entropy and information rate. Right. Now, so we know that entropy of the source is the weighted average of the entropy of a symbol emitted from each state. So the entropy of a state, any state I, can be defined as the average information content of the symbol emitted from that particular state. So now you see, we bring in the concept of state, but anyway, let me write a point here so that I can make it clear when I explain, right? So the entropy of, okay, let me write a source first, then I'll bring the concept of a state. Okay, entropy of the source is defined as the weighted average of entropy of the symbols emitted from each state. Okay, now I'll come to the concept of a state. Now you see, let us assume that we have uh, say there are two symbols that are being emitted from a message source, like 0 and 1. Okay, so you see that the 0 and 1 may occur with, anyway, we know that there is a probability of 50%, that's half and half. Let's assume it can change also, it can be 1 by 4 and 3 by 4, or any other value, 1 by 4 and 1 by 5 and 4 by 5, like that. You can have any probabilities, but what is the chance that if I get a 1 after 0, you see, right, you have some certain probability, this is different. Similarly, if I get a 1, what is the probability that next I am going to get 1? If I have a 1, what is the chance that I am going to get a next 0? If I have a 0, what is the chance that I am going to get a 0 again? Now you see, every value depends upon the past value. So in the sense, in order to get a 0 now, you may have to check what is the chance that previous value was 1, because 0 to 1 there is a possible transition like this. So you see, each output is associated, or each of the outcome or each of the symbol is assigned to what is called as a state. So that's why we try to define the as uh, entropy as a term that is calculated by using the state of state of the Markov source, right? So Markov sources will be represented by uh, these kind of diagrams. We call them as a state diagram. So we have to use a state diagram in order to define or in order to represent the Markov source. Okay, so anyway, I'll come to the diagram later, but I need to justify that why I use the word state here. So what is a state? State is used as a term to represent that and symbol is being emitted. Every symbol emission is associated with the state. Okay, the word used is state. Okay, now each state has an entropy. That's what is the meaning of this. Average entropy of symbols emitted for each state. Each state has certain entropy. Now I'll define, right, what is the entropy of state I, any state, right? Entropy of the state I is, say, normally we denote Hi, right? Entropy of state I is Hi, comma, let's try to define. Defined as the average information the average information content average information content of the symbols of the symbol emitted from that particular state. Okay, so now we know this I can write an equation. Hi is nothing but from that particular state, uh, whatever is the number of symbols that you emit. Let's say I am trying to emit h is equal to 1 to n, right? This is pi. I'll write pi log to the base 2 1 divided by pi. Okay, probability of that. Now entropy of the complete source, right? This is hi we understood now. So this implies, let's go back to the definition, right? It says that entropy of a source is nothing but weighted average of entropy of the symbols. In the sense, in terms of I should write the total h. Okay, so that's the difference between the previous cases and the Markov source. Okay, so I'll write the entropy of the source is the average of hi. It's a weighted average. All right, so I'll write hi is equal to, it's a weighted in the sense multiplied by the probability. So I is equal to 1 to n. This is pi into hi. So where pi is the probability of a state, okay, and n is the total number of states. All right, so this n should be different from the previous n. So okay, well, let me make a change. This is pij. I'll write a pij in the previous equation. Just make a note, right? I'll write a pij. It's a probability of jumping from ith state to jth state. J can be any other states possible. Like if I have 3 states, you see here, pij will be 1 to 2 and 1 to 3. Whatever these jumps you can do, or even 1 to 1. If you have these jumps, they are the required probabilities to be used from a state to the all other possible states, including itself. So that's what we are going to use. Anyway, we'll solve the problems to make things very clear to you, right? Okay, so here where the pi is the probability of ith state, then the rest of the concepts will remain pretty much similar. Uh, that is, if you want to calculate average information rate, So that is denoted by capital RS. That is equal to, use the same equation, small rs into capital H, right? Small rs is, it's called as the rate in which the symbols are going to arrive. H is the symbols, sorry, bits per symbol, so that you get the units as bits per second. Okay, very similar to the previous. Uh, Now, the next concept is average information per symbol. This is also an important concept. So that is average information per symbol of a Markov source. Right. So let us start with an assumption that there is a notation P of Mi. Okay, is the probability. It's a probability of a sequence. Okay, sequence A denoted by Mi of, let us say there are n symbols in that, right? N can be 3, like ABC, right? ABC are the 3 different symbols clubbed together to get a sequence, and the sequence is ABC, which has 3 symbols, so n is equal to 3 in that case. Okay, from the given source. So here the source is definitely Markov source, right? Now let us try to calculate like this. So the average information per symbol is denoted by Gn. Okay, a G of n symbols, right, is nothing but 1 divided by n times summation over I. This is probability of Mi into log to the base 2 of 1 divided by probability of Mi. So basically this is nothing but, right, this will be the nth extension of the source divided by n. Okay, so h of s is the entropy of the source. Okay, let me write entropy of source. So here the summation is taken. If you look at the above summation, summation has to be taken over all the sequence mi's containing n symbols. Okay. So now there is one very important property that we need to discuss. That is, uh, that's very important. This is important. So limit as the n increases. Increase, I'll show it as n goes towards infinity. The Gn will reach the h itself. Okay, whatever h we have calculated. So bits per second. Very important thing. So whenever we'll solve certain problems, we'll be able to see this. Okay, we'll verify this. But normally, any problem that is based on the Markov source will be pretty lengthy because you have to calculate a lot of probabilities. Then use the probabilities to get the probabilities of each state. Use the probabilities of each states in to calculate the values such as the entropy of every state. Calculate the entropy of every state to calculate the H value. Okay, entropy of the whole source. So there are so many things to be calculated, so which is what we are going to see.